Cool. Hello, everybody. It is fantastic to be here. A massive thank you to the organizers and the sponsors for making this happen, and of course, for you all here to turn up today. So hopefully, we'll have my slides up. Wonderful. So I'm going to be talking about memory management in Go, the good, the bad, and the ugly, and that is because there's so many dimensions to memory management in Go. Now, I admit there is a ton of different abilities in the room, so hopefully there is a little bit in this for everybody here. So a little agenda, what I'm going to talk about is some key concepts, so we're all up to the same level. I'm going to talk about what memory actually is and what it means to you and me. The Gopher approach, how Go really attains to memory management, some memory leaks, and how you can potentially optimize it for the better. So a little bit about me. Who am I? Well, my name's Liam Hampton, and I'm a Microsoft Senior Cloud Advocate, and I work in the Dev Tools team. So anybody who's used VS Code, anybody who's used Code Spaces, Copilot, any of those cool tools at Microsoft, that is what I'm a part of, so I help advocate for those. I'm an also ambassador because I really like talking about security and identity and helping you all understand how you can think about that first and foremost as opposed to just writing some code. I write Go code, obviously that's why I'm here, and I like to travel the world. I am an avid traveler, sounds pretty cliche, but I became a developer advocate so that I could travel the world. So let's talk about some key concepts. So Go is a fantastic language when it comes to concurrency. When you want to run multiple asynchronous, say, methods in Go routines, this is a wonderful language for it. If we think about the shift to cloud and cloud-native computing, I think Go was dubbed the networking language of the future, of which I totally agree with. It's fantastic. It's type-safe, so it's kind of like a portable debugger for you as you type, or as you code, rather, because it prevents you from making silly mistakes. So if you install the Go plugin in VS Code, you'll actually be able to see this. It won't let you compile or run your code as, well, if there's an error in it, right? Cross-platform compatibility is a huge bonus with Go, so it allows you to test and build for different platforms, whether it's Windows, Mac OS, Linux, whatever. It supports a whole bunch of operating systems and architectures. With that, it enables you to test and just build great platforms. The standard library is phenomenal, so you can pretty much code or create anything you really want from the get-go just without third-party imports, which I admit is brilliant, and you don't often get this with other languages. And a big props to the Go team for making this even better. So in the recent releases, they have been improving the standard library over and over again, and it's wonderful to see. And finally, garbage collection. Go has got this wonderful garbage collector, which allows it to have a really minimalistic memory footprint. And that's what we're going to dive into a little bit with today. So when I was a software engineer and I was writing a lot of code in a team, I was working on a really memory-hungry and CPU-hungry application. I'd never learned Go at this point. I'd never touched it. I was coding in JavaScript, and that was a bit of a beast in its own. One of the other engineers said to me, Liam, how difficult and how hard is it to manage your memory in Go? Can you learn it? Can we do something with it? And it lit a light bulb in my head and was kind of like, yeah, sure, let's figure this out. Let's go and investigate. I'm very much a self-taught programmer. I didn't really learn much at university. I don't really have a computer science background as such. So I found this as a learning curve, and a steep one at that. So if I was to ask you what memory is, you'd probably come back to me and say it looks something like that, like a memory, like a RAM stick, and you'd be totally correct. There's nothing wrong about that. But as a software engineer or somebody who writes some code, I look at memory a little bit differently. I look at those sticks, and I break them down into little chips. Going a bit further, we can see that those squares are literally just ones and zeros. Now, this is important. When you look at this, I kind of see a housing estate, or lots of houses in a group. Now, the ones could be occupied, and the zeros could be unoccupied. So as you start coding and declaring variables and moving them around and starting Go routines and creating your wonderful programs, you're moving data in and out of those memory locations. So a house that could be occupied could then become unoccupied, and so forth. Now let's look at some base systems. Here's 4 common base systems that we use as humans. So we've got base 2, which is binary, ones and zeros. We've got base 10, which is what you and I communicate in, so 0 to 9, and then so forth. And then you've got base 16, which is hexadecimal. Now that is 4-bit bytes, and that goes 0 to 9 and then A to F. Now the funny one on the end is octal, and that is 3-bit bytes. So that goes 0 to 7, and then skips a couple and goes 10 to 17, and so forth. That's just using 3 full-bit bytes. As humans, we focus on base 10 and base 2. So a light switch is on and off, is binary. And base 10, if we want to tell somebody how old we are, we say it in base 10. But a machine would typically use base 2 and base 16. Base 2 being binary, and base 16 being hexadecimal. Now, hexadecimal is 4-bit bytes, and they do this because it's a little bit easier to communicate with. So let's take this as an example. Base 2, that is an 8-bit byte, and that is 8 ones. Imagine a system trying to move that around every time you want to do something. And if you were to read some memory heaps or some stacks, and it was full of ones and zeros, we wouldn't be doing our jobs, because that would be too hard to read. So we want to convert that into a base 10. It's going to be 255. And anybody who's written CSS would know that 255 is FF, which is white. So it's not only cheaper for a system to move 2 4-bit bytes around, but it's also easier to communicate with us. So we use that system instead. Why does it matter? Why am I telling you about base systems? Well, when you look at memory and these housing estates, or housing estates that I'm going to call it, they have addresses. So each location has an address. And if you're going to be looking at an address, it looks something odd like this, like a 0x123. So bear that in mind as we go through this. So let's park the bus on that one, and let's move on to some bad memory management. So with bad memory management, you can get some really big issues that arise, most namely, some awful bugs. So I came across something, a problem, when I was coding, when I was first learning Go a few years ago, and this problem sticks with me today, because it's a really good example of how a really annoying bug can turn into something of a learning curve. But with those annoying bugs, you can introduce memory leaks, and memory leaks can start stealing all your memory. So if I had a 128 gigabyte sticks in my massively overclocked machine, what it's going to say is, Liam, you're not using all of that memory, I'm going to start using it for you. And ultimately ends up crashing your application. And if your application crashes, your container could crash. If your container crashes, I don't know, a virtual machine could crash. And it just becomes this long knock-on effect of a chain of really expensive errors. And ultimately, leading back to the first one, where a developer has to go, what am I doing? So how do we mitigate that? How do we look into this? Well, there's different ways. Manual memory management is one of them. So if you're familiar with writing C, you'll see here, we've got a couple lines of code. It uses malloc. Malloc is memory allocation. Now, to you and I, that's a bit of a pain, because in these couple of lines, I've already got a bug. I haven't freed it at the end. So with C, you are manually allocating memory and deallocating it, and you have to keep track of it. As an engineer, as somebody who's writing the code, you have to know where that memory is, what has it, what's in it, and how you manage that. Well, that's a bit of an arduous task. So what about automatic memory management? Well, that's a thing too, and that comes with different languages, and every language seems to do it a little bit differently. Java does it differently from Rust, Rust does it different from Python, Python different from Go. So before we get into Go, I just want to go through how Python manages memory. So it uses reference counting. So every single time an object is referenced in Python, it increments a counter. And every single time it decrements it, every time it unreferences it, it decrements the counter. And when it reaches 0, it's good to go. They free it up. And it uses a cyclic garbage collector. Now, that is just a fancy way of saying uses CPython, and it kind of reduces the amount of times it has to run a garbage collection cycle, meaning it doesn't interrupt the code as much, which is fine. But then how does Go touch it? How does Go do this? Well, Go uses a stack and heap. It uses a garbage collection as well, and it uses pointers and references. So what's a stack? So a stack is comprised of stack frames. Now, I look at this as a stack of books. If you stack them up next to you, and you want to get the last one that you put on the pile, it's going to be the top. And that'll be the last one you put there. So it's last in, first out. Now, it's usually fixed in size. However, with Go, it's a little bit different. So Go runs with Go routines, and Go routines have their own kind of stack, should we say. Now, they start pretty small, about 2 to 4 kilobytes, and they grow, and they grow, and they grow. And sometimes it can borrow from the heap. And the heap is what we're going to go into next. But essentially, a stack frame is the state of execution of your code at any point. It stores the function call, and it stores the local variables in that frame. Anything that is then saved goes to the heap. So it's kind of like a temporary memory, should we say. The heap, on the other hand, is very much more dynamic. It's not fixed, and therefore it's much slower, and it's a lot less efficient than the stack. Now, I think of the heap as more of a room, where you open a door and you throw the book in the room. If you ask somebody to go and pick the book off a stack, they'll be able to find it and pick it off very quickly. If you ask them to find it from the heap, they have to go into a room, search all the books on the floor, bring it out, and give it to you. It's much slower, but it's much bigger, much more dynamic, and a lot more flexible. It does a lot of the heavy lifting for you, and it stores all your big data types. So whether it's a pointer, whether it is an array or a slice, it stores that in the heap. So how do we manage it? So Go uses a wonderful garbage collector. Now, a garbage collector is basically saying, don't worry about managing your memory, don't worry about those mallocs and the frees, I'll do that for you. So it picks anything that is of nil value or is out of scope, and it will dereference it and just sweep it away, get rid of it. Now, it uses a pacer and works off of a trigger ratio. Now, a trigger ratio is, I'm just going to read it from this extract from the docs here, is a collection is triggered when the ratio of freshly allocated data to live data remaining after the previous collection reaches this percentage. So basically saying, when it reaches a certain threshold, run a garbage collection cycle and free up the memory. Now, that's wonderful, and you do have control over this. You can change this. I personally have never changed it, and I probably wouldn't ever go to that unless I'm working with sort of low-level code at the memory level as it is. But you can do it, and it's really good. And the final part of this is it runs concurrently. Now, running concurrently would often mean that it doesn't really interfere with your code, and that's good. But there are two times when it does. So there's two major phases. You have a mark and a sweep. Now, it uses stop the world when it goes before the mark phase of an object. So when it sees a dead object and it wants to mark it to be swept, it will block it then, and after the mark phase as well. So once it's done, stopping something from writing to that memory, ready to be freed up and released, and then straight after it's finished doing that. So think of it as kind of like a friend in a group chat. They just silently sits there, reads everything, doesn't really interfere, and pipe up when you only want them to. That's what a garbage collector really is doing. So for the visual, or visual representation, we have our memory that looks a little bit like this. Now we've got our ones and our zeros, the occupied and unoccupied, we've got our memory addresses, but let's move away with that, and let's turn it into this. Let's say they have streets. Now, in this housing estate, we've got streets. Some are machine code, so what's always running, your very low-level code. You have your global variables. You've got your heap and your stack. This is a very simplistic way of looking at this, by the way, but this is a really good illustration of how it can work. So we're only going to worry about the heap and the stack, so the very bottom part of this. The stack is going to ultimately grow up, and the heap is going to grow down. So we have this fluctuating bar in the middle between heap and stack. What happens if you start touching memory that is not allocated to your program, that has no business being there? Say you go to another town and you start setting up camp. What's going to happen? We're going to have a problem. You're going to have an issue. And the way that the Go garbage collector really works is by following that around, following your program, and just sweeping it all up and helping to prevent that from happening. Of course, you can run into problems, and this is a very simple example, but it's very much how it works. So every single object which you have, Go will go around, the garbage collector will go around, and it will check it, even the really long-lived ones, and will sweep it if need be. So this is very different to Java, where Java uses a very general garbage collector, and it passes every X amount of times, but it won't always check every object. But it keeps reference of that. So every language does it a little bit differently. So quick show of hands in the room. Who is familiar with writing C code? All right, cool. So that's about half the room. Brilliant. Well, I sympathize with you, because even though Go is a high-level language, you still need to be aware of pointers and references. What does that mean? Well, when I was first learning Go, I ran into a few bugs, and it was pretty much because of these. I had no idea what I was doing. I didn't understand it from beyond face value. So throughout the conference, if you see somebody's slides and it has an ampersand, it means a memory address. If it has an asterisk or a little star, it means that it's dereferencing it to the value at that memory address. So it's going to the root of the memory address and finding the value that's held there. So a quick example. So Liam's number is 27. and I admittedly have probably called this the worst thing, calling it pointer, but a variable pointer is equal to ampersand of Liam's number. Now I'm going to print those two out. I'm going to print out Liam's number, or sorry, pointer, and the dereference value of pointer. And as I'd expect, I get a memory address and 27. Now as you can see, this memory address is being written in a funky code. Imagine if that's ones and zeros. That would be awful to read. It literally points. That's what a pointer does. It points to somewhere in memory. So same example, same code, just a little bit different at the end. So we're taking the dereference value of pointer is equal to the dereference value of pointer plus 2. So it's all good knowing that you can access the memory and you can see what's living in the memory, but what can you do with it once you have it? Well, you can do some arithmetic. So as I expect, I get 29. And that's right, only the cool kids do maths this way. And this was a really hard concept to gather as I was starting to learn Go. Why is this happening? Well, it's because I'm changing the value at the memory location. I'm not changing a copy. So here's the issue that I ran into a few years ago when I was first learning. So this is a really simple function, and I've got variable x and variable y. X is 1, y is 2. And I'm going to print them out. So that first print is 1 and 2, as I'd expect. I'm doing nothing special. I've just declared the variables, and I'm going to print them out and say, what's there? What have you got? But what about that second print? So in between that second print and the first one, I've got a swap function. And the swap function is typically going to swap these values around for me. So imagine we have a glass of red water and a glass of blue water. If I want to pour them and switch them around, I can't just pour them into one another because, well, it will spill. It will create a mess. So for the visual learners in here, we're going to add a third variable. I'm calling it temp. So for this, I'm going to say x is now temp. So temp is 1, x is empty. Empty. It's not quite, but it is. And then I move y into x. So now x is 2, y is empty, and temp is 1. And then we're going to switch it around again, and we're going to put the value of temp into y. So now x is 2, and y is 1. Awesome. That works, right? If the print line was in this function, it would print that out. That's what I'd be expecting. However, that's not the case. I still get x is 1, y is 2. Now, people who have written Go would probably understand why this is happening, but I wasn't changing the value in memory. I was simply just changing a copy of those variables. So here's the fixed code. And this took me a while to figure out when I was learning a couple of years ago. So the first thing I'm doing is I'm passing in the pointer to the memory address of x and y. So rather than taking a copy, I'm taking a reference. I'm then dereferencing it in the swap function and saying, hey, go to these values in memory and grab the root value. And then we're going to do the same arithmetic, swap them around, and then it should print it out as expected. And I'm going to come back to that at the end with a short video. So now let's talk about memory leaks. Now, memory leaks are a lot less common in garbage-collected languages, purely because the garbage collector helps prevent them. That's the purpose. But a memory leak is when you no longer need the memory, and it just doesn't get freed up. So it's kind of like a squatter in a house in our memory, in the estate. Now, I ran foul of this very recently. 2 examples. The first one was a Go routine that I never terminated properly. Now, that was just taking up memory after memory after memory, and it was allocating variable after variable and just not terminating. And that's a very common use case, and I see that quite often. And I personally ran into this myself. And a second example is not terminating a connection to a database. So I was writing a bit of code, and it was calling the Azure Cosmos DB, and it didn't terminate the database because it was failing. So that connection held onto memory, and it just didn't let it go. So even though my code had failed, it still held on to the memory. Now, this is where not using the defer keyword properly comes into effect. Now, defer simply means defer a closing of a connection, so whether your code passes or fails, at the end of the block, at the end of that execution, it will always terminate the connection. And that's what I learned from this. And Matt did a fantastic presentation of the defer keyword a couple of years ago for London Gophers, and it's stuck with me ever since now. So how do you find these memory leaks? How can you spot them yourself? Well, you'd be surprised the amount of conversations I have where people do not read the tooling. They don't use it. So use monitoring tools. You've got Grafana, you've got your cloud providers, you've got Amigo, you've got tracers that you can plug in, OpenTelemetry if you've ever used that before. So you can really read into the depth of what's going on at every point in your application. And if you see a graph that just continuously goes up, well, then more often than not, you may have a memory leak. Now, for the more savvy in here, read the heap sample. If you can spot a pattern, if you can see a function that is continuously adding to the heap and it's not being deallocated, you may or may not have a leak. Investigate it. So that's a really good way to look into this. So remember, whenever a function is called, that goes on to the stack, which is the stack frame, and if anything is saved of a variable, of a pointer, or anything like that, it goes straight to the heap. So check that out. So how can you optimize code? Now, with optimization, there is always trade-offs. Now, when you're finding optimization, you've got to find the golden path. You have to find that middle bit where it makes everybody happy. Because ultimately, if you have a team of senior developers who are going to write the most optimal code, that's wonderful until you introduce an intern who has no idea what's going on. A good example is some code here. This is nothing special. This is just a function which is adding some names to a slice, and it's going to go around a for loop and add something extra into that slice, and then it's going to do it again at the end. It's going to append it. So this could lead to a situation where reallocation occurs multiple times. That's kind of leading to memory allocation being used up unnecessarily. Not the end of the world, could be better. So if you look at some optimized code, where you allocate a larger slice up front, this avoids repeat allocations and the copying. So it's better, it's optimized to an extent, but for the sake of this, when I read that, it's a little bit easier to read the one on the left than it is the one on the right. So when you're optimizing code, just always be careful of this one. And as a result, it can be costly. So like I mentioned, if you have these senior developers, which are always writing this really cool, hardcore code, and it's great and wonderful, it can be costly in time because you might be working for a startup who needs the next feature for your next Series A. You've got to think about the balances at this point. And it could be counterproductive. Now, I worked in a team where somebody was doing this, and they were a great engineer, by all means. They were absolutely fantastic. However, once they had optimized the code, they introduced a load of caching and a lot of buffering, and ultimately led to a lot of memory utilization and kind of reversed what they were trying to do. And it was pretty fun to see that because they spent so long doing this, and it was kind of like a, ha, I told you so moment. But you get this all the time. You just got to be careful of what you're doing. Now, how did we spot that? How did I know, or how did I find out that it was using more memory? Well, I used pprof. Now, pprof is a wonderful tool. It's built into Go, and you can see it here using the omit, and it's in the NetHTTP package itself, so it's already there for you. Then you can run this in a Go routine and just have it sat idle and profile exactly what it is that you want to do. So if you're running some code, maybe like a port scanner locally, and you use a for loop consistently to try and find some open ports, and then you switch it to use a Go routine, you can kind of see the differences between them. So once you spin it up, once you're using this, you'll get to this portal. I say portal, it's like a very static website. And this is on localhost, and it gives you the option to go in and jump in and see the allocations. So we can see there, allocs. So mallocs is very similar to C. You've got blocks, you've got Go routines, you've got the heap, and you can go and read all of that. Now, if you dive in and look on the right-hand side, that stack is what it looks like. And it looks pretty awful, and it's pretty annoying. And if we were all reading that, we'd take forever. But if you install GraphViz, like an external package, I think, you can get a web UI which looks much better. Now, this will tell you all the time that your code is spent executing, and you can see the next step that your code has taken in the stack. So each of these just jumps down each frame as you go. And you can jump in and see a lot more as well. So who here has used flame graphs before? OK, a couple of you. Good. So quick overview, a flame graph is a really good way to show you how optimal your code is, or how often and how long your code is spent executing. So along the top, we've got time present. So that's the time present your code has spent executing. And down the bottom, or down the side, we've got the stack depth. Now, that is how many times your code has been called. So that's not the same stack that we've been talking about in memory. This is stack depth, as in this is a stack. Now, they're grouped together, so you can see this is sort of ordered in alphabetical order, so it's not everything happened in this function, then everything happened in that function. It happens sporadically. This is just how it's grouped. Now, you can change this as you wish. You can group them as you like. This is a really good way to see at a high visibility and, well, virtually, how you can see your code is behaving. Pretty awesome. Some top tips of optimizing your code. Avoid using global variables when possible, or where you really don't need to, because they are the permanent squatters in your memory, and they sit the global chunk. Use the defer word or keyword appropriately. Always close your connections. Make sure you're closing them. Get them right. And then always reuse your objects when possible to avoid reallocations, because ultimately that's just going to create a lot of churn in your code. And I couldn't leave today without talking about some AI. So we all know that generative AI is pretty much taking over the world right now, and there's a number of examples. So we have ChatGPT, which you're all familiar with. So that's kind of like GPT-3, 3.5, 4, etc. Kind of, you ask it a question, it will answer your exam for you. Jack of all trades, master of none. And then the one that we have at Microsoft, the one I'm most familiar with using, is Copilot. Now, Copilot is based on OpenAI Codex, which is an LLM specialized in code. So what can it do for you? Well, it can help explain your code, it can help write your code, and it can help fix your code. Now, if I had this a few years ago when I was learning Go, it would have been so much better. I would have not been stuck on that bug for as long as I was. So let's watch a little video, how you can interact with Copilot. There's two ways. Now, the first way, I'm not going to introduce any new code at this point, because there's no point, I don't want to confuse anyone. So same code, same issue. This is the unfixed version. So typically you do a comment and you write a question or a Q and a colon. This is the question or correct way of interacting with Copilot, and it will give you an answer. Ultimately, if you're not feeling like doing that and you're a little bit lazier, like me, you can just whack it in the comments and it should be smart enough to tell you exactly like that. So that's the first way you can interact with Copilot. And now let's go ahead and fix that code using Copilot Chat. So Copilot Chat is now actually in public beta. I believe it was released from GitHub. And we've got the same problem here. And I'm just going to say, hey, can you help me fix my code? And the day it comes back and says no is when I'm going to have a problem now. So I'm going to be relying on Stack Overflow for that one. And of course it says, yes, I will help you fix your code, Liam. So how are we going to do this? And I'm saying, you don't need to be a prompt engineer to figure this one out. This is like a conversation that you just have with ChatGPT just inside Visual Studio Code. So I'm saying, when I run my code, it's not swapping the values like I thought it was. And this is in real time, not sped up, by the way. And it gets a bit dizzy after a while. But what it's essentially done is saying, you know what, Liam, you're just taking a copy of the values. You're not changing the memory address. This is your problem. And here's the fixed code. So not only has it explained it, it is fixed the code, and it is then given me the code as well. Now, admittedly, I'm not a fan of the variables that it's given me here, but then that could just be down to my poor variables to start with X and Y. But all I've got to do is copy that across, both the swap function and the function call itself. And then all I have to do is go ahead and run it. So I'm going to open up a terminal, and I'm going to say, you know what, here's the proof in the pudding that that code works. As we'd expect, it's nothing special, but it's a really good purpose of how you can use AI for good, or how I'm using it as a developer. Now, this is a very simple example, but you could go way beyond what I'm using at the moment. But what not to do with AI? Just use common sense, really. Do not stick your API keys in. Don't start giving it personal data. You wouldn't commit that to your Git repository. Why would you give it to an AI model? And secondly, don't always assume it's correct. Now, this is something which we're seeing now, and I'm having good conversations with people around, is people are taking this at face value and thinking that it is the best thing, and it is always correct, and it will give you the right answer every time. Now, anybody who has copied and pasted from ChatGPT will probably know that is not the case. I'm foul of that as well. So when you ask a question, always query the answer that you're given. So let's look at the good, the bad, and the ugly. Well, the good is, when it comes to memory management in Go, if you're learning it for the first time, or whether you're a seasoned developer, you have a lot of help. There's a lot of help to be given to you. The bad can be quite tricky, because you always need to understand what's going on at a system level. You need to understand what's really happening underneath face value of your code, i.e. pointers and references. And then the ugly is, well, it can get pretty messy pretty quickly, and it can get quite complicated, but don't be scared. So if there's anything that you take away from this today, and I hope it's answered or made more questions than given answers to, is just don't be afraid of memory. Don't be afraid of querying. Don't be afraid of printing stuff out and trying to read in and dig into it. Give it a go. It's your best friend, especially when you're writing Go. So with that, I want to say a massive thank you. And if you have any questions, then connect with me. I'll be hanging around. Thank you very much.